Good evening. Welcome to this session, handling billions of messages with the PrestoDB in the country of pyramids. I am Ravishankar. I work for PassionBytes, United States, Florida. About me, I'm working in the data warehousing, ETLs, and big data for quite a long time, different industries across the globe. Most of my time was in the financial industry and then slowly moved into healthcare, transportation, retail, trade, and logistics. Yes, since the inception of PrestoDB, I am taking a lot of pride to be called as a Presto evangelist and working on some of the improvements in PrestoDB as well as doing some implementations across the globe. Well, if you have noticed the title, handling billions of messages in the country of pyramids, I just wanted to emphasize that pyramids. Preciseness, even 4,500 years ago, it was amazing to see the great pyramids in Cairo. It's not only big and huge architecture, but it is the aesthetic beauty of that architecture which attracted me more than the size. The foundation, of course, is solid even today, and I think another 4,500 years it will and may exist. Uh, and it's not just that pyramids that's important. It's again great to see that along with the pyramids, that whole ecosystem, the chapels, the temples around it, and the tombs, etc., etc., it is that which makes it so nice. And this man made wonder, and the client asking for something to deal with massive ingestion of data, the pyramids motivated us that we should be trying something solid, and we need a similar ecosystem like pyramids which is also solid to address it. And of course, as a propagator of the PrestoDB across the globe, my first intention was to take this particular challenge and try to solve with PrestoDB if at all possible. Well, before they even approached us for handling this particular requirement, there were many experiments and POCs completed on this particular part, but nothing was satisfying and giving a query performance which was querying about 100 billion to 150 billion rows in a quite satisfiable time. The SLA was not met, and there were challenges in storage as well as achieving what exactly they wanted. So let me just start by looking at the problem statement. This is related with a telecom company, and as you know, on the right hand side, the towers different at different places, they receive the electromagnetic and the waves from the mobile phones, and whenever we make any calls or we browse, etc., etc., and then that data goes to a base station, and from the base station it goes to the carriers, a central network place where they collect all this data and also transmit to other telephones, etc., etc., right? And from this particular telecom data, they can get the statistics. Okay, how many people are using which particular service, how many people are gathered around a particular place, and it can also help for promotional activities, if they want to, in order to make sure that that complete data is utilized. So basically, millions and millions of rows, right? And adding up to billions of records per minute. And the estimated volume that we get, including the peak hours and non-peak hours, to be handled, about 15 columns of data like call start time, call end time, the service, the IMEI number, etc., of the telephone. Those data amounting to about 120 billion. And we need to query it satisfactorily. And they told that, okay, the querying time for different filters and different analytics, etc., can be within 8 minutes to 10 minutes. That was the challenge that was given. But it should not be ever more for this particular massive volume. And what we also heard was the latest and the closest value they could get for a simple count star query was about 20 minutes in some of the commercial solutions. We should be able to do analytics further on the top of it. Maybe huge data you might be pulling into a notebook. You need an efficient mechanism to do that. And also, if suppose there are some existing BI tools, they want to connect on a slice of data, they should be able to do it. So that's the problem statement. And we are in the country of pyramids, starting to attempt this particular issues. And let us just go through some of the steps that we had gone through and how we arrived at a very simple and elegant solution which is satisfying the needs. So let's move on. The first thought, as you see Googled or you might have experienced this kind of circumstances, the first thing that will be coming in is, oh, why can't the towers, the telephone networks data that can come into Kafka is proven for trillions of messages at Twitter, etc. And then why can't we use a very big, huge Kafka cluster? Maybe we can have a Spark or Flink connecting to that particular Kafka and take the data and store it in some ORC format, for example, and then let a query engine like Presto, which can also massively query this particular data and then get that, right? So that was the first experimental thing. And this part of the diagram that is taken from one of the Spark conferences, I don't remember, either 2019 or 18. And please look at an experimental setup in one of the presentations that they have done. And the total size of the data was about 12.8 terabytes and 128 nodes, which means that basically about 100 gigabyte of data. And then we have one, not the cheap or not the weakest hardware, but we have got nice, pretty neat hardware, as you can see, 512 GB RAM per node. And it has got, of course, the non-volatile NVMe disks, SSDs. And it is an RDMA connector. It is not just a kind of 1 gigabyte or 5 gigabyte kind of network, but it has got a direct memory access connector, 100 gigabyte, right? And then the experiment shows, and for not this much amount of data, and we have done something in the ranges of about 2 to 3 terabytes as well. And I'm just since I got this example, which is taking larger data, I'm just quoting this one. And you can see that if 100 gigabyte is the network speed, the program could achieve not even 5% of it. And the red colored part, shaded part on the right hand side is the actual network speed that we got, even though it is 100 gigabyte network. This is a very common and very unknown fact that the full utilization of the network is not being used while we are preferably dealing with big data kind of data transfers and that kind of volume of the data that is needed to be transformed. Well, what can be the reason? One is the serialization of the incoming data into a network understandable format, and then the deserialization of the data at the receiving end. The next one is most of the Java based frameworks, which are which really are today, they have they are using a lot of serializers, including the native serializer and then some cryo kind of serializers, sorters, etc., while the data is being transferred. Always the network admin says us that, you do an FTP of 1 GB of data from one machine, one node to another node, and you look at the speed, you should be getting this speed, but we won't. And the reason is the Java-based frameworks are using these complex sorters, serializers, etc., while transferring the data, and they are very expensive operations. Given this particular massive ingestion of the data that is required, and that data has to be transferred into the corresponding delivery point or the storage point, even if we use a high fast computing framework, which might be doing a micro batching, and then going through this kind of serializations and giving us less network usage, increasing the latency, and then delivering the data is not suggested. Hence, we did not go through this particular path. Instead, we looked at a simple JDBC connection in Presto, and there also we faced an issue. If you look at the code, PrestoDB JDBC connectors are single-threaded, which means that whenever you are connecting to an Oracle database or a MySQL database, the connection is single-threaded. It connects from one of the workers where the plan is scheduled, and then it gets the data, and then comes the rest of the framework activities. Is there any way that the JDBC in Presto can be made as a push-down parallel query engine like Spark? For example, if you look at the Spark code and look at the lines from 25 to 34, and then you see how the data is getting pushed, you can see that we can give a lower bound and upper bound, and we can create the number of partitions that we require, and so certain data types are supported for the partition column, and then when we write the query, actually the query is getting pushed into the number of queries that are getting generated by dividing upper bound minus lower bound divided by the number of partitions. In this case, 0, 150,000, and then there are two partitions, so it will be dividing into two queries, and then the two queries will be executed in parallel. This is the default behavior if you are enabling these properties in Spark. So what we did is that we used a JDBC driver, a Presto JDBC driver, on, let's say, an ORC-based file system, which is exposing a table through Hive metadata, and then try to write this particular query by pushing the minimum key and the maximum key. Amazingly, the speed was very, very fast, and it created the multi-parallelism that was not by native available in Presto, but this particular framework allows it. Again, the problem is that here we are not querying a database, and we are going to query something where we are going to store the data. So before we query the things, let us see how we can ingest the data. So this problem of network utilization, the less network utilization, was in the industry for some time. And it is at that time that we noticed this tweet from Wes McKinney, uh, the Pandas fame, who told that the future is Arrow. And why is it so? When we started investigating on Apache Arrow and the corresponding ecosystem in more detail. So, a quick start if you are hearing Apache Arrow for the first time. On the right hand side, if I want to take a data from the database and then read it from the application and put it into a network NIC, traditionally, a system call happens between the database and the kernel space, and from the kernel space to the user space or the application space. And then the user space gives a copy back to the kernel space, and the kernel space gives back to the network card. So you can see that there is a user space and kernel space involved in a copy of the data. This is good and it is not significant as long as we are having small data. But when you are having big data applications and when you want to store more and more data, this might not be the efficient way. That is where the concept of zero copy is coming in. And it is there in the industry from a long time in the operating systems. For example, Linux has the send file 64 system calls, send file system calls. Java has got a transfer to method rather than the file method using the NIO channels, etc., which is doing not a for context switch based copy, instead just two copies, as you see in the below part, where we are not transferring this and this. That means two context switches are getting eliminated, and we are telling the user space or the address space or the application space to directly copy the data from the kernel space to the other kernel space and then give it back to the network. And also, if you are finding out some method by which serializations and deserializations can be avoided, now you got a global format which uses zero copy so that the network utilization becomes much efficient. And that's what Arrow is doing, again, invented and monitored and developed by Dramayo and Wes McKinney. Now, Arrow is a data format, and to transfer the data built on the top of protocol buffers and gRPC, the Arrow ecosystem contains something called Arrow Flight. So, Arrow Flight is a protocol. Flight is a protocol and Arrow is the data format. So if Arrow data is transferring through the Flight protocol, then we get all the benefits that we mentioned about the zero copy and also some improvements in the deserialization and serialization of the data. And it is having the support for bidirectional streaming, which means that many clients, when they are getting flight info, another client is getting the flight data back, and this happens in parallel. And the bidirectional streaming, which is built on top of HTTP2, it is supporting you the streaming of the messages until the messages are complete. So stream of the data can be returned back to the clients, and it supports concurrency as well. You can read the below link given in order to get more details about it. So basically what we are getting here is create the data in Arrow, create a flight server just like the thrift connector in Presto, try to register that Arrow file into the flight server, create a Presto flight connector and read the data. And what you get is very high speed avoiding almost the serializations and deserializations and the problems that we have mentioned. So the approach is depicted here where we used Spark again and then created an arrow RDD, right? Just like your JDBs, RDDs, and all those things. And then register that arrow RDD to a flight server, which is running separately. And then PrestoDB has got an arrow flight connector we built, and then try to connect from the flight server and read the data. Absolutely fantastic. The performance improved a lot, but not too much. Again, it has got some issues which I'll discuss at a later point in time in this presentation, where the data read was getting blocked after reading 100 to 300 million. That one, maybe still we are using Spark to read it, and it has got the same serialization problems for the first time to create that arrow RDD from a normal CSV file that is coming from the tower, right? And then another problem might be that, the network between the Spark cluster and the flight server and the PrestoDB connector, too many components, maybe something we can avoid. So we try to think that why do we use an arrow RDD? Instead, can we use a normal file system, as some of the blogs and links are suggesting, along with the Presto, maybe a Parquet or ORC format, etc., etc. And also, this particular experiment gave us another new idea that now with this arrow flight connector and flight server, any code which can give me an arrow RDD or an arrow file format, which easily can be done in a Python, Ruby, or 11 languages that are being supported by the arrow ecosystem. All these languages, any code can be registered into a flight server, and you can connect with the PrestoDB arrow flight connector. That means you are basically getting the ability to invoke any code written in any language through this approach as a, the data store. So the code is becoming a data store, and then Presto is pulling it. Anyway, the next attempt was looking at the blogs. Again, we have a nice blog in the PrestoDB about the Parquet 2 writer, that is the modified Parquet writer. And one of the advantages of the modified Parquet writer is that it uses Parquet 2, the next version in the Parquet file system. And if you see, you can see that there is some aggregated minimum and maximum values for every page Parquet is keeping in the Parquet 2 format. So when you are querying, if the query is within those limits, then the Parquet file system can respond very fast. Less time will be taken for scanning the pages because you have the minimum and maximum, and you can search it for much, much faster. So now our problem reduced into a small issue. We need to create Parquet files from the data that is coming from the tower. And if we are able to create that data very, very fast, then our problem will be resolved. Now, we are going to use Parquet 2 format, but if we are trying to create a partitioning and sorting mechanism, thinking that that would be benefiting our storage, of course, it will benefit the storage, but we saw that a lot of time is taken for partitioning and sorting. Even though generation of the Parquet file can be made faster, but if you are trying to do partition on a phone number column or a date column, etc., that will create some issue. So finally, what we thought is that we won't do any partitioning. We will not be looking at any sorting either, but we generate Parquet 2 format very fast, unsorted, and unpartitioned. So basically what we have done here is that in every database, if you look like Oracle or MySQL, etc., the read operations and the write operations are happening within the database ecosystem. But here, what we are doing is the read operation will happen from PrestoDB, whereas the write operation will happen from some simple Python script using arrow-based libraries, creating the Parquet 2 and writing to an object storage so that we are having fault tolerance, replication, active passiveness, etc., the data security, etc. So we selected an object store for writing the data. So coming to the architecture and little bit of coding, you can see that what we have done is we wanted to create the Parquet 2 file format very, very fast. As you can see clearly here, we are using the arrow format and generating the Parquet 2 file, which is very fast than the usual way of creating an Parquet 2 file. And then we are going to embed this particular Python file that you see on the left-hand side, minio python.py, which basically creates the Parquet 2 file from the CSV files that are coming in and then writing it into Minio. And we are just giving you the code of how to do that. And we are using all the default values of Minio installation, which is an object store. Then we repeatedly write that particular data and put it into an object storage. So now you got the object storage data. In PrestoDB, we will configure that object storage to be read. And as you can see, we are not using an explicit metastore. Instead, we are using the same S3 environment with the Presto schema as the metabase or as the metadata. Rather than using a MySQL metadata-based catalog database. The reason is that we wanted to eliminate whatever minimum time that we could save by extra connections. So we used the same S3 bucket for that purpose. So the overall architecture, all the CSV data is coming into an NFS share. We use two machines, 96 core vCPUs with the code that we have explained earlier. Using the arrow format, using Parquet 2, we wrote it into a distributed Minio active passive replication NFS drive. And wherever you see NFS, we were careful to use SSDs. And the network connectivity was about 100 gigabits per second. And then from the Presto cluster, we configured the Hive connector to read that particular data. As mentioned earlier, the ingest cluster is different from the query cluster. Once this is complete, a small issue, we started querying and the data is coming too fast, and you can see here 147 billion rows, but it was taking 15 minutes. We tried looking a little bit later and we see that the number of splits is not much increasing and the query time is becoming more, 18.41. And clearly this is the time where you need to scale PrestoDB. So we used three machines, 512 GB RAM each, memory intensive, and now we got the result in 3 minutes from 3 nodes. One of the things that you may need to look is a dstat output while you're writing the data, and you can see that when you are writing the data, there are a lot of idle time. The CPU is idle, and there is a lot of wait time, and there is read write happening, but you are not expected to see, or you should not be seeing this kind of values. This wait time should have been very, very less, almost zero, so that no wait is happening and the CPU is working. That's what we want. So this indicates that you need to have more improvement, and that is when we changed it to the Parquet 2 and arrow-based format using GNU parallel in order to write the data out. And the final query, 572,000 files almost was ingested into the Minio object store, and we got the query of 562 billion in 8 minutes at the end of the first day. The client is satisfied, and we got the result and we are waiting for or looking for the next steps. That's all from me. Thank you very much. Any questions?
Thank you so much, Ravi. Great session, a lot of great information. Great to see Presto scaling really horizontally across the board from one node to three, and dramatically taking down the latency, the query latencies there. In terms of the arrow integration and basically outputting into that format, how much of a performance improvement just did that element of it, outputting in arrow format, give you?
Actually, that is the main thing where we succeeded, Diti. If you observe that, the generation of that Parquet 2 files. So what we did is we used the operating system's parallel command and then generated that using arrow, which was giving me about 35 to 40% improvement than the usual methods of using, the normal framework like Java or something like that to create that Parquet 2.
Great, great. Well, thank you so much for your session today. Let's move on to the next session, which is in another room. Thanks again, Ravi. See you again at
Thank you very
future.
much. Thank you. Thanks a lot for the
Cheers.
opportunity and great to be with the Presto community. Thank you.
Thank you.